So my name is Jerome. I'm part of the ZKM development team. I'm cryptographer, and I'm going to talk to you about hybrid rollups using MIPS instruction set. So I think we all know, we also saw it in the previous talk, the usual problems with layer one. It provides a scalability, security, decentralization. Well, not really. Scalability is sort of a problem. That's exactly the trilemma. So layer one doesn't scale well. There's no privacy, and it may lead to high gas cost. So how do you solve this? The solution has been around already for some time. It's called a rollup, which essentially means that you shift all the workload from layer one to layer two while maintaining layer one security guarantees, right? So that does mean that for the data that the transaction data, we're talking about processing transaction, right? Payments. You keep the data in layer one, but you compress it. You compress it because that makes it cheaper to maintain it. Otherwise, the gas cost is going to be high. And you're going to maintain the overall state also in layer one. And so you minimize the data cost, but you do processing, you do all the processing on layer two, which is the layer that you are the owner of, so you don't pay for it, or at least not that much, and you register results on layer one. Now there are basically two strategies for doing this. The first one is called optimistic rollup, which means the following: you provisionally validate all the transactions, but you have another entity which are called the challengers. And the challengers, they are scrutinizing the blocks that have been published on the blockchain. They scrutinize and they're going to verify to see if the results are correct. Okay, so if a challenger finds a mistake, it's going to say, hey, this sequence, this batch is not correct. And in that case, there is a special, what I call an arbitrator contract on layer one. And so the batch gets sort of scrutinized by some arbitrator, and the arbitrator gives a verdict whether the batch will be valid or invalid. And in the case of if it's invalid for sure, there will be some sort of punishment, right? So I like to call this the challenge game, because this is some game theory going around here. You have parties that are incentivized by using, I don't know, Ethereum probably. If the transaction is not challenged, then it will be considered correct at the end of some time, some challenge period, which is typically 7 days. And the 7 days is sort of, before I get there. So here we get an overview of the whole system. So the sequencer gets the transaction and decides which the order, he creates the batch, right? The batch gets sent to the blockchain. And actually, the challenger, in this diagram, it says that the data is sent to the challenger, but actually the challenger is looking on the blockchain in the compressed form to verify the batch, and it's going to do the check, the scrutinize the batch, and then it's going to say, well, it's valid, then there is no problem, and after some time it will be validated. If not, then there is the arbitrator contract. And then hopefully it gets valid. So the X here should be a V. Okay, so what are the problems with optimistic rollups? Well, you consider the transaction valid until proven otherwise. So you must trust that the challengers, the people that are scrutinizing, that they are diligent. You must sort of trust them. What if everybody is asleep and wrong transaction gets approved? You don't want that. So it's also, when I saw this for the first time, optimistic rollups are counter to what blockchain stands for. You want the blockchain to be right. You don't want to have a mechanism that can say, yeah, it's probably right unless somebody says it's not. So it's counter, yeah, it's counter to the whole philosophy of blockchain. And an important point is that for many transactions, a processing time of 1 day or 3 days or 7 days is simply not acceptable. It's simply too long. So we have a second strategy, which is turning more popular now. We also saw it in the previous talk, which are called zero-knowledge rollups, which is based on verifiable computing. So what is verifiable computing? Well, in this context, it means that the layer 2 computes the new state, but in addition, it provides a proof that the result, the new state, has been computed correctly. And this proof is succinct. It's short, which means that the verification of this proof by layer 1 is, so the proof is short and the verification is orders of magnitude faster than the computation itself. Right? So the idea is that you gain because now layer 1 doesn't have to do the computation, it only has to do the verification of the computation, which is supposed to be much faster. Okay? So this is the slide that corresponds to this approach. You get now that it's like the sequencer and the prover, or the proof generator, they are sort of friends, right? So the data gets sent from the sequencer now directly to the prover. The prover creates a proof that the new state is correct. This new proof is sent now to a specific contract, which is on layer 1, which verifies, so layer 1 at this stage verifies the correctness of the new state. It sends its verdict, should be correct always, to the bridge contract, which then publishes the new transaction state. Okay, so this is the strategy for ZK rollups. So what are the properties here? Advantage that the validity proof, once confirmed by layer 1, you know that it's valid. I mean, there's no discussion anymore. It reduces the time to finalize the transaction to hours. Because it's hours, it's not instantaneous, unfortunately, because the proof generation time, generating the proof, as I showed here. So generating the proof, this is a process that can take 1 hour, 2 hours or something. So that's quite intense, right? To create the proof, which is easy to verify, that by itself can take a couple of hours. And there is huge complexity in this case. There's complex mathematics behind. I like it. I'm a mathematician, so I'm having fun. It's difficult to implement. There are other people in the team who like to implement, so they are having fun as well. So what are hybrid rollups? Well, this is essentially just the combination of the two rollups we had, so the optimistic and the ZK rollups. They can coexist and they can be unified. Why is this interesting? Well, some clients may not trust CK rollups in the beginning. They may, I don't know, have qualms about it. Some clients may like a longer approval time. You know, if you have a transaction of, I don't know, millions of dollars of worth, then maybe you don't care if the transaction takes a day because maybe you change your mind in the middle. So some clients, they like that. So what we imagine here is different transaction categories. So a client can choose, oh, I want an optimistic, or I want a ZK or hybrid. You could do both, which will result in different latency and different fees. So I'm from the technical side. This is from some commercial argument. I'm not going to go into the details, but this is something that can be explored. Oh, and here we have the slide that combines it. To be frank, I think it's easier to understand the two previous slides. This is just both slides superimposed one to the other. The only thing is that, you know, here at some point you will have this commercial thing that will make the choice in what kind of rollup the client is actually using. So the question that you can ask is, what is the language that you are going to use to program? I said you need verifiable computation to verify the transaction. So what is the language that you're going to use? And so our team decided that MIPS would be a good choice for this, to implement the verifiable computing. Why? Because it has been around already for decades. It's got a strong presence in industry. It's very generic. Anything compiles to MIPS. MIPS compiles to anything. And it hasn't changed over time. You know, the EVM bytecode, sometimes there are little minor opcode changes. RISC-V allows for custom instructions. So a specific company, they want, oh, I want this extra instruction. Now that's fine, but if you are implementing zero knowledge, then that means that for each instruction, you will need extra work. So we value the stability of the MIPS instruction set. So this is a very high-level overview of our MIPS processor. On the left, we have 32 registers. We have some specific registers, high, low, and a program counter. We have a CPU, and we have here, this is the memory. Now, so we're under the hood, right? I'm showing some details. So what we are envisioning is that you have your MIPS program. You have the ELF loader. ELF is the binary, the executable and linkable format that's a standard. Then you use the MIPS virtual machine. Now the MIPS virtual machine, you may have some opcodes that are interacting with the operating system, things like that. So you need some stubs, you need some solutions for that. And the result of that is what we call the execution trace. I will be showing a short example of that in the later slide. And the execution trace will go to the proof generator or the prover, which will result in the proof, so the ZK MIPS proof. In a particular context of layer 1, we can show these details. Let me try this. No, it's not working the way I want. This should be state, 5 should be state, should not be batch. So what happens is that Well, this is the extension of the diagram that we showed already. We just blew up this part, so you get here inside, you get the batch monitor, you get the state monitor. Batch and state go to the MIPS virtual machine, which produces the execution trace, and this is really the cryptographic part that will make the cryptography resulting in the ZK proof. The ZK proof goes to the smart contract, and we're done. Oh. Someone left his back here. So this is what's called the execution trace. What happens here is the following: that any program execution on a processor, you can envision it as, the processor has got a specific state, and this state is in every step of the processor, the state is changing, right? So this is how you can model in program execution. So you have here on the columns, you have all the variables from the processor. On the rows, you have each opcode, and each opcode will change a state. I mean, this is not shown in the diagram, but if you have an add instruction, for instance, maybe register 1 will go to a new value. Okay, so that's the idea here of the execution trace. And then the step, the usual step, it's going to be superficial, okay? But what happens is that the prover, the prover generator, he converts the execution trace to a giant polynomial, right? The polynomial, the degree of the polynomial can be like 100,000, 1 million, or even up to 1 billion. Beyond that, I don't think we can process that. So the prover, layer 2, yeah, he's the powerful guy. He generates his polynomial, and this is a lot of work. But the idea is that the verifier, the layer 1, has this verification contract. It verifies the properties of this polynomial, so there's some magic going on, that the constraints on the computation should be reflected by the properties of this polynomial. And this verification process is supposed to be very efficient. Okay, so this is the arithmetization. I'm going to be high level on this part. We are using STARKs not because they are post-quantum resistant, or because of the setup ceremony. That's we want STARKs because they are fast, actually. So the performance of STARKs is good. The way there's more detail in the white paper, there's a specific slide, a specific diagram in the white paper. This says that we switch from STARK to SNARK. We are using Snarky and Plonky 2 in the first it's Stark, and then we switch to Plonky 2. And we use, I didn't include that, we use proof recursion techniques, you can combine various proofs into one proof, either using recursion or using batching. So that was under the hood. I just want to generalize the part about the applicability of ZK MIPS. So the general setting of verifiable computing is that you have a weak party, right? The weak party wants to outsource a computation, but doesn't trust the result. So besides the fact that it gets the result back, it also wants a proof that the result was computed correct. And so the weak party goes to a strong party, and the strong party does all the work, and gives back the result together with a proof that the result is correct. And then we can put this in several contexts. So the context that I just described is that we have the layer one is sort of the weak verifier, and what it does, it wants to verify the computation that's been done related to the transaction. So it goes to layer two does all the work and sends the result back to the verifier. You can think of it as computation, you know, a client with your notebook, you can do it in the client. Note that, right, independent of the processor of your client, this could be a MIPS program, right? It can be MIPS that's generated on your PC. So this is going to the cloud. The cloud does it work, and you get the execution result and the proof. You get it back. Other examples. You know, you have to think of examples with weak systems that need to do computation with a strong, that want to outsource computation. So you can have wearable devices, embedded systems that interact with the service provider. Other cases that have been discussed already in the past is that the user wants to verify a database. We have the specific example that Vitalik talked about in Bogota, when he said that, you know, you want to be able to download maybe a big file from the internet and verify it with a couple of checks on your smartphone. And as a last example, now the weak party actually is on the other side. So you could have a physician that's querying a database, and the database, well, this is about machine learning. So there's, you know, machine learning, AI under the hood there. And in the first scenario, the machine learning model is giving an output, but how can the physician trust that the output was computed correctly? We can envision the use of MIPS to create proofs that the output of the machine learning model is correct. Which leads me to the last slide. So to summarize, I will be talking about hybrid rollups. Optimistic and ZK rollups can coexist, can be unified. Hybrid rollups combine the best of both, right? Okay, so the solution that we are proposing, it can be with any layer 2 solution, right? And besides the layer 1, layer 2 context, ZK MIPS has other application, as I just showed in the last few slides. So if you want to check out the details, I think the white paper is going to be published on Thursday. It's going to be published on the ETH research webpage. So maybe you have to refrain your curiosity for another 48 hours. Okay, so that's it.
Thank you, Jeroen. Do we have any questions so far?
Hi, thanks for the presentation. I have one question. On one of the slides, it says some clients might like longer approval time. So I was just wondering what kind of clients like longer approval time?
What do you mean?
On one of the slides, it says the difference between ZK rollup and optimistic rollup. It says some clients like longer approval time.
So for optimistic rollup, the
Yes.
approval time usually is a couple of days, which is up to 7 days.
Why would some client like longer approval time?
For the newer version.
Like why?
Why?
Yeah. What?
Use case for optimistic.
Yeah.
I don't know. I mean, this is the way the policy that has been defined. So people give an opportunity for the challengers to scrutinize these blocks.
Yeah, that part I understand, but it says clients like longer approval time. I would assume everyone wants it to be settled as soon as possible, right? The transaction.
Sorry, I'm also from the ZKM team. The answer is if you're transferring.
You had another
And
one?
we found that to be the case with large institutions. For you and I with a small bag, it doesn't make a difference. It makes a difference for bigger bags.
But I don't think you can like cancel that transaction, right? Even if it's not.
His thought. Go ahead.
Never mind. The next question is, so does the current version you are building for the liquid rollup require the multi-party setup ceremony?
What? Sorry, can you repeat that?
The ceremony, the setup ceremony for the liquid rollup. That's the.
We don't need one.
The current version
Because
doesn't need
no,
one.
we're using Fry, so we don't need it.
Okay, cool. Thank you.
No, I mean the argument is there, but we don't need a setup.
You don't do the setup?
No,
I see.
no. We can use Fry, so Fry is hashing based. But
the final layer is not, so you still need
what's that?
the final layer of your proof is not.
Yeah, well, the problem with that is what you call a snark and when you call a snark and a snark a stark. So, but because it depends on two things, right? The arithmetization can be based on a processor, like that I'm showing, or it can be based on circuits. So the snarks, they use circuits, the starks, they use the processor. Right? Now, traditionally, also the snarks are based on KZG, right? On the KZG commitment, whereas the starks are based on Fry and on hashing. Okay, so when I said snark there, I meant to say that we are using, in the beginning, we use Stark, then we go to Plonky. Plonky is circuit-based. So this is why I said we are using snarks. But this is not the bit commitment that we are using.
You always using Fry.
Yeah, we use Fry. Okay?
All right. Thank you very much.
Thank you.